Great. So our next speaker is Marc-Olivier Renou, who's going to talk about why quantum theory needs complex numbers.
Yes, thanks a lot. So, well, I'm quite sure we cannot imagine how hard and stressful it was to organize this conference in person with COVID, so thanks a lot to all the organizers. Yes, so today I will talk about this paper with my co-authors, and I think a more precise title would be Real Number Hilbert Space Quantum Theory with Tensor Products is experimentally falsifiable. So I will explain what I mean by this. But first I want to start with a very simple experiment in which we have, for instance, two states shared between three parties measuring those states. And if we use quantum theory to describe what's going on, we'll use complex number operators. So the question I want to ask here is, why not real number operators? And what would happen if I had real numbers? And actually, this question was already present at the very beginning of quantum theory. So for instance, when Schrödinger found his equations, he was quite unhappy with the fact it was using complex numbers. Okay, so actually this question is a bit naive, and there is already a very easy answer, which is to say that when you do an experiment, you are just considering statistics of experimental results, and somehow those statistics, you can describe them using probabilities, which are just real numbers. So somehow if I had a book containing all the probabilities of all the potential experiments, then I would have a fair description of quantum theory using real numbers. But today what I will discuss is something a bit more precise. I will discuss theories in which we predict and explain what is going on in experiments. And the theory I want to discuss is the standard theory of quantum, the standard quantum theory, in which I have the Born rule and those complex operators. Okay, so let me be more precise about what I mean by complex number theory and real number theory. So my complex number theory is the standard one in which we have states, which are positive operator in a complex Hilbert space, which trace to 1, and then I have projective operators for the measurements. I have the Born rule to compute the probabilities, and importantly, when I have two systems, the Hilbert space describing the two systems is just the tensor product of the two Hilbert spaces, and if I perform independent preparations of two systems, I have a tensor product of the two states. So this is standard quantum theory, and what I call real quantum theory is just exactly the same theory, but now I replace complex Hilbert spaces by real Hilbert spaces. Okay, so the question I want to ask is, do a real quantum theory and complex quantum theory have the same experimental predictions? So what I will show is that it's not the case. But before showing that, I want to make two important remarks. The first one is that actually there do exist real formulation of quantum theory. So the first one was my book containing all the probabilities, and I also have more precise theories in which, so for instance, I have Stuckelberg formalism or Bohn's formulation, which can be made real, but of course they don't satisfy my axioms. So I'm really discussing those axioms. And then another important remark is that there are already arguments rejecting real quantum theory. So the first one is experimental. I can just prepare a state of some finite dimension and try to see how much degrees of freedom I have access to in this system. And if you do this, you will see that you have access to too many degrees of freedom according to real quantum theory, so real quantum theory is wrong. But of course, to do this experiment, you need to trust that you have a state of some finite dimension. And somehow this is infeasible. Experimentally, any state you will create is always infinite dimensional because you always have infinitely many degrees of freedom, for instance, the time of emission, the direction, many things. And then there is another argument, which is more theoretical, against real quantum theory, which is local tomography. So in quantum theory, in real quantum theory, I have some states which are bipartite, shared between two parties, such that I cannot characterize the state by performing local measurements. So if I add local tomography, then I reject real quantum theory. But here what I will prove is that this is not needed. Already with those axioms, I can reject this theory. Okay, so to explain our work, it's quite interesting to see it as a game between a theorist and an experimentalist. So in my game, I will have a complex quantum theory theorist playing against a real quantum theory experimentalist, and his goal will be to find a challenge. So a challenge for me is just an experiment with a state and measurement operators associated to a probability distribution. And then the experimentalist will try to take up the challenge, which means that he will try to find a state and a measurement in real quantum theory which reproduces exactly the same probabilities. And then the theorist will look for a good game, which is just a game where the real quantum theory experimentalist fails. So you should be all very familiar with this, because this is exactly what we have in standard Bell games. In standard Bell games, I have the same theorist, but now he's fighting against a local hidden variable experimentalist. And we all know that there is a very good game, which is this CHSH game, in which we have an experiment in standard quantum theory, in which I have 2 square root of 2 at the CHSH score. And of course, we know that the experimentalist, if he does something which is a local hidden variable model, he will find a CHSH smaller than 2. So this is a very good game for the experimentalist, in which the local hidden variable model experimentalist fails. So somehow what we need to do is exactly the same, but now in a context in which the experimentalist is allowed to use real quantum theory. Okay, so I will tell you first that in a large family of games, the experimentalist can always win. So I will first present games in which the experimentalist wins, and then I will present the one in which he fails. So a first game is the following. So it's a very naive game. There are a lot of ways to simulate, but I will give a precise one. And so the theorist will just think at a well-chosen state and well-chosen measurements, sent to a box, the state, measured with the measurement, and he tries to find something which is not simulable. So there is an easy way to always simulate this, which is the following. So the experimentalist can introduce those 2 states, and just remark that the second is just the complex conjugate of the first. So for now, this is an extra qubit, which is again complex, and then he will introduce this new density matrix, which is just the initial one, right here, tensor with I, plus the conjugate tensor with minus I. And the same for the measurement. And it's quite easy to see that if you try to conjugate this, you will exchange the 2 terms. So in the end, you find something which is self-conjugated, hence real. So of course, the structure of this is quantum, but then if I look at it and I write it in a matrix, I will have only real entries, right? So I really have something which is part of real quantum theory. And then if I apply the bond rule, actually it will be conserved. And while it is the case, you can take the theorist's point of view, and you can interpret this state as composed as the initial state plus a flag, which is I or minus I, and then the measurement operator will first measure the flag, and if the flag is plus I, then he will apply the standard measurement, and if it is minus I, it will apply the complex conjugated. So this flag somehow is indicating what is the value of the square root of -1, and as the measurement box have access to this information, the bond rule is conserved and everything works. And then, of course, the flag alternates with 1/2 probability between plus and minus I, such that the total state is in R. So this challenge doesn't work. I could go a bit beyond and try to introduce this kind of experiment, but again, there is an easy way to simulate this, using this state in particular. And here the idea is that I still have this flag, and this flag is correlated. Part of it goes to Alice, part of it goes to Bob, and as at any stage Bob and Alice have the same definition for the square root of -1, the probability is conserved. Okay, so to go beyond this, we need to make this flag particle trick impossible. But of course, this is not enough. I'm not fighting against only this simulation. I'm fighting against any possible simulation, possibly in infinite dimension, or possibly something which is not corresponding to a kind of flag particle. Okay, so now I come to the challenge which is infeasible, which is the following. So now I will consider three parties sharing two states like this. And actually, I will make an additional assumption, which is that the experimentalist should respect the same experimental structure. So he should also find two independent states, so those two states are independent. He should find two simulating independent states such that the probability is conserved. And then in that context, it's quite clear that the flag trick cannot work. Because if the experimentalist wants to distribute a flag, he needs to use a source which is not there. And he has access only to two independent sources, so he could try to distribute a flag with this source and that source, but of course, the flag in that case would not be correlated, so with some non-zero probability, Bob will have different value for the square root of -1, and this is problematic. So of course it's not enough, because if my states are just noise, I will not detect anything, right? So how to select those states? So the way we did it is the following. So the state we took are just maximally entangled states, 5+, and then we ask Alice to perform those standard poly measurements. So you see that the last one is complex, and Charlie to perform those one. And we also ask Bob to perform a Bell state measurement in the standard Bell basis. So this is just the measurement which is used in entanglement swapping or teleportation. Okay. So now I will give some ingredients about my proof. So our proof is linked to self-testing. So it will be understood by people who knows what self-testing is. For the other, you can just wait one slide and just catch up after. So the main ingredients of the proof are the following. So if you observe the probability distribution obtained in this experiment, you can see that actually a lot of versions of CHSH inequality are maximally violated. So for instance, if you consider the case when Bob obtained 0, so projects over 5+, Alice and Charlie obtain share 5+, and then as Alice is measuring Z and X, and Charlie is measuring Z plus or minus X, they obtain a maximal violation of CHSH. And actually, there are a lot of symmetric versions of CHSH which are hidden there. So now, if I imagine that the experimentalist could find a simulation of this, of course, he should also obtain the same maximal violation of CHSH. And with CHSH, we can apply a lot of self-testing results. So in particular, we can apply this paper in which there is what I call a 3 CHSH self-testing. So in practice, what I can show is that actually, if Alice is performing some real measurements, then in some sense, she has no choice but to use the what is -1 flag strategy. So I started from a potential measurement in infinite dimension, but now I know that she is performing the what is -1 flag strategy. And then if I look at the full setup again, I can also apply a second paper in which we can prove from the statistics that Bob is performing the Bell state measurement. So using self-testing, I can really self-test the fact that the parties are performing the flag measurement, and also that Bob measurement is not compatible with the full probability. Okay, so this is just the arguments, the main arguments of the proof. Okay, so in the remaining time, I would like to discuss briefly experimental tests. So in our experiment, we ask source independence. So this is, of course, very problematic experimentally, because if you want to make an experiment in optics, for instance, you will align some lasers of the two independent sources, but of course, by aligning lasers, mirrors, etc., you may introduce correlations between the two sources. So actually, we could prove that our result is still valid if you have classical correlation between the two sources. However, of course, it is not valid when you have quantum correlation between the two sources, because in that case, this quantum correlation can be considered as the global source going everywhere, and you can do the flag simulation I presented in the beginning of my talk. And noise is also important, of course, in experiments. So we do have a Bell-like test, so a generalization of CHSH score, which can make a clear distinction between the two theories, even if there is noise. And well, at last, there are 3 experimental demonstrations which have been done. So a first one with superconducting qubits. So I'm not an experimentalist, but it's very unclear for me if we can really justify the source independence in this paper, because it's 2 supraconducting sources on the same chip, and it's not clear for me that the 2 sources are independent. Then we collaborated to a photonic experiment in which we perform a new protocol based on the partial Bell state measurement, and there is a last one which implemented strict locality conditions. Okay, so I am done. I only have 1 minute, right? Okay. Well, I'm almost done. I will take my time. I thought it was 20 minutes, but okay, good. Yes, so we have proven that quantum theory needs complex numbers. So more exactly, it does not work with real numbers, right? And our proof relies on the axioms 1 to 4. This can be witnessed experimentally. And well, as I have more time than expected, maybe I can discuss a bit this source independence justification. So I think that at the theoretical level, it's really fair to assume that I should have a simulation with real quantum theory which has the source independence, because in my axioms, I have this tensor product rule. When I create 2 independent systems, I say that the matrix should be a tensor product of the 2 independent states. So of course, if I have this axiom, it means that in reality, I should be able to place myself in this context. It should make sense to consider an experiment in which I create 2 independent states. Because if not, I would not need that axiom, right? But then, if you think at experiments, you need to check that this is the case in your experiment. So if you perform a photonic experiment, for instance, you need to ensure that your 2 sources are independent. So you could, for instance, use SPDC sources, right? So you could use the same SPDC source to crystal to create the 2 sources. So you create a first pair of Maximilian entangled state, and maybe a bit after you create the second. But of course, if in your crystal you have some quantum memory effect from 1 to the second time you use the SPDC, you will introduce quantum correlation between the 2 sources, so this is bad. So you can try to use 2 SPDC sources, okay? But then maybe in the same laser you are using to like pump the 2 SPDC, you also have some quantum correlations, which is bad again. So you could try to use 2 different lasers to pump your 2 SPDC sources. But here again, you could say that actually you are using the same electricity supply to power your 2 lasers. And in your electricity supply, you have quantum correlations going to the lasers, going to the source, etc. So this source-independent hypothesis, in practice, is very unclear. It's not clear when it is satisfied or not, and somehow it is you believing that it is satisfied or not in your experiment. Okay, and to conclude, I would like to discuss potential future work. So a first direction which is interesting for me is that to remark that those 4 axioms are very mathematical, so it would be quite nice to have something which is more physically motivated. And I mean that, well, there are several works in which quantum theory was reconstructed from principles, so for instance this and that work, and it would be quite nice to understand the link between this theorem and those reconstruction. And then another direction I find quite interesting is this one. So we know that Bell-like tests can reject local hidden variable models, so this is just Bell theorem, can also reject real quantum theory. This is the result I just presented. And the question which could be asked is, what theories can be rejected by such experiment? And could we eventually imagine that we can reject any potential theories except quantum theory? So can we find a list of tests, concrete tests, such that if I obtain exactly the correct score at all these tests, I can say that quantum theory is the unique theory which can explain my correlations. So this idea is, for instance, presented in this paper. So I also have a work in that direction in which we rejected the possibility to explain quantum theory based on any generalization of bipartite quantum states plus shared randomness. Okay, so with this I would like to thank my colleague and I'm happy to take questions.
Use the microphone.
So I have a...
Can I have the slides, please?
Okay. I have a question and a comment. Which one you would like to have first?
Well, as you want.
Okay, the question is, of course, you say you cannot, real quantum physics cannot simulate the complex one with the right locality structure, of course. Okay? But what about if I ask the following question? I don't want locality structure. I just want one state. Yes, I have observables, just like in the beginning you listed, but I do want something more, because among my observables, some of them could be simultaneously measured. And I want to respect this with my with my real simulation, Can you do that?
I'm sorry, there is a very bad echo, but I think I understood. So you said, what about a simulating experiment in which I have only one quantum state?
One quantum state, several observables. You want to simulate this sorry, not classically. You want to simulate this with real quantum, but what you want to preserve is the structure of simultaneous measurability. Can you do that?
So the flag simulation is not doing that?
I don't know.
I think it is. So I think the first way to simulate I presented is working. So the way you will simulate your state is by adding an extra qubit, which takes the value plus I or minus I, and which is distributed to all your observables. And then one observable will first measure the flag, and then apply the initial projector or the complex conjugated. Right? And this is real for sure, and I think it preserves what you want.
Okay, I have to think about it. I don't see it. And the comment, this is just a comment that even when I was a physics student, and I asked questions like, complex numbers, then the usual kind of answer was somewhat different, and it relied on representation theory, namely that you have rotations in our Euclidean space. You have isotropy, and so you want to have a representation of the group SO3. And now, what about real representations,
yes.
complex representation?
Yeah, so it's a good question. So, yes, sorry, there is an echo, so from here it's very hard to... Yes, so it's a very good question. So actually what we have done is really device independent. So when you say I perform a rotation in SU2, SO3, you say, okay, I have something which acts, which rotates the system, but what we have proven is robust, even if when you think you are doing a rotation, actually the operation which is implemented in practice has nothing to do. So for each angle, if you want, you would have something which is completely different, right? So you rotate a bit it's adding a lot of degrees of freedom, you rotate a bit more, it's destructing them and doing something else, right? So really, the proof we have
Yes, I understand this is more. This is completely independent of such. I'm just that's why I said that this is just a comment that is usually about usually they mention the rotational symmetry because, of course, the representations of SO3 in real space are completely different. So you can easily pinpoint
yes, but
certain...
okay,
We'll have to continue this discussion offline now. So we're over. I apologize. We need to move just to stay on schedule.
Is there more time for a second question, or is it?
I mean,
it's fine. If not, it's not. Yeah, I guess it's a quick question.
Quick question.
Yeah, you had this quote where you said, you know, the wave function should, or it would be nice if the wave function were real, right? Something to this effect. It's paraphrasing, but what are why should we want the Hilbert space to be over real numbers? Like, is it just a matter of us preferring real numbers over complex numbers, or is there some other reason why we might want that?
So, okay, there is maybe an answer, and this is why Schrödinger, I think, was quite unhappy with complex numbers, which is the fact that before quantum theory, there is no theory which was expressed with complex numbers at the very beginning of the formalism. So, for instance, if you think at electromagnetism, of course, when you have a propagating wave, you will use complex numbers because you have this rotating wave, right? But the first formalism is Maxwell equation, and this is in terms of real numbers vector field. So somehow quantum theory was really the first theory in which, when you were writing the very basic equations, you had complex numbers. And yes, well, this is a bit perturbating.
So it's like...
Thank you.
Okay.
Let's thank Marc Renou again.